If we place a car at the top of a ramp, it will have a certain amount of gravitational potential energy. When the car is released, the potential energy will be converted into kinetic energy and the car will move down the ramp. Now so far, there's nothing here that's particularly surprising for anyone. Falling objects speeding up is an everyday experience. But in physics, we can do far better though. Instead of just saying the car will speed up, we want to predict exactly how fast it will be going at the bottom of the ramp. If the car is 14 centimeters above the light gate as shown, how fast will it be going when it reaches the gate? You can actually do this without knowing the mass of the car, but here it is anyway to give you a bit of a help. Now I'd like you to come up with a prediction for the speed at the bottom of the ramp. Then you'll get a chance to carry out the experiment and test how well this works in practice. When we talk about the height of the car, what we're really talking about is the change in the height. So how far has it fallen? So to calculate this value, you have to measure the starting height of the car and then subtract the final height just after it's passed the light gate. This is because the car doesn't go all the way to the bottom of the ramp. Light gates can be used as part of an electronic timer. To detect an object, a beam of light is directed at a sensor. Whenever an object is under the gate, it blocks this beam and the sensor receives no light. When an object passes through the gate, the beam of light is blocked. When this happens, the timer starts counting. After the object is passed all the way through, the light reaches the sensor again and the timer stops. We have the time it took the car to pass through the gate. To get the speed of the car, consider the distance it moved during that time. Shown here, you can see that the car moves the length of the car's fin. We can measure this with a ruler and then use the equation speed is distance over time to calculate the speed. We have an equation that allows us to calculate how much energy the car was given. We also have an equation that allows us to calculate the energy it ends up with from its speed. Without something else though, without a link between these two equations, they're rather useless. But if we make an assumption, if we assume that all of the potential energy gets converted into kinetic energy and kinetic energy only, we can do much, much more. Now this is an assumption, that's why it's physics rather than maths, but that's not a bad thing. Making an assumption to get rid of irrelevant details is a very, very important part of physics. There's nothing wrong with that, but you must be very clear whenever you do it and state it in your working. But now that we've done this, we can predict the speed. So assuming the final kinetic energy is exactly the same as the initial potential energy, we have this equation. Swapping in the full expansions for that, we have 1/2 mv squared is equal to mgh. Now there's a mass term on both sides of this equation, so we can cancel those out. And also we can multiply both sides by 2, so we end up with v squared is equal to 2gh. Finally, take the square root of both sides, and we have an equation that will allow us to predict the final speed. Now remember, this is only true if we have this assumption. If there's any energy being lost, this will not hold. So that's the theory and most of the math. Now we can actually go and test out some of the assumptions that we've made along the way, as well as some of our predictions. So the first one was for a change of height of 14 centimeters, the speed of the car should be about 1.66 meters per second. Carry out the experiment several times and see how good that prediction is. We've also assumed that there was 100% energy conversion. Test that. Third, the mass of the car doesn't actually determine the speed according to the proof. So see if that's true. And last of all, maybe the height of 14 centimeters is special. Maybe that's not a fair test, so try some of the other heights.